Alright, so we just worked an example of a series circuit. Now let's work an example of a parallel circuit. So, again, just like in the series circuit, if we weren't told this was parallel, how would we know that it was? Well, if we just look at our circuit diagram, we can see, as we leave the battery, we get here and there are options. Options means parallel. So we could either go down through R1 and be back, or we could go over through R2 all the way back to the battery, or through R3 and then all the way back to the battery. They are in parallel with each other. There's nothing else to this circuit. Those are all of the pieces. It's purely parallel, 3 resistors in parallel. Again, I like to start these by making a grid, a little data table. So let's put total, R1, R2, and R3 on our data table. And what are we going to find for these things? We're going to find V, we're going to find I, and we're going to find R. And then after we're done with those, we'll go back and look at power as well. So what can we fill in? Well, off the bat, we can see our battery voltage, or the total voltage, is 3 volts. We're also given resistances for our 3 resistors. R1 has a resistance of 3 ohms. R2 has a resistance of 4 ohms. And R3 has a resistance of 12 ohms. All right, so that's where this problem starts. Well, what are we going to do next? We're going to simplify it. That's always the next step to take. And these are all in parallel with each other, which means that we can combine them all into one single equivalent or total resistance. But how do we do that? Well, we just did it in series, and it was straightforward. You just add them all up. In parallel, it's a little bit trickier. Equivalent resistances are given as the sum. Equivalent resistances are given as the inverse. 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. And these are always going to be a little trickier to add up. As I said in my notes, I recommend just using a calculator. Let the calculator do the work for you, particularly if you are uncomfortable with adding fractions. Because what do we get here? 1 over R1, you get 1 over 3 ohms plus 1 over 4 ohms plus 1 over 12 ohms. And now if we wanted to add these, we would need to get a common denominator. And so for those of you interested, you multiply the top and bottom by the same numbers, all in an effort to get the bottom numbers all the same. So the least common denominator between 3, 4, and 12 would be 12. We multiply by 4 over 4. That's 4 over 12 plus, to multiply, to get 4 to 12, we multiply by 3. 3 over 12 ohms. And then 12 is already 12, obviously. And that's what we would rearrange this to. But please don't do this if you don't feel comfortable with it. You can let your calculator do all of this for you. Once you have a common denominator, that will stay the same. 12 goes straight over. It's the same in all of them. Then we just add across the top. 4 plus 3 plus 1 is 8. But your calculator would do that for you, so please put it to work. 1 over R total then is 8 over 12 ohms. Are we done? No, we are not done. We need to flip it. We need to get R total equals. We flip it and we get R total equals 12 ohms over 8, or 1.5 ohms. R total is 1.5 ohms. And I forgot to mention it earlier, but you guys may have noticed when we added up resistors in series, the total resistance got bigger. When we added up resistors in parallel, that total resistance got smaller. That's not an accident. That always happens in that fashion. All right, well, our total is 1.5 ohms. We can add that to our data table. 1.5 ohms for our total. And now we have a spot. One spot with two other pieces of information. We can solve for I total. I total is going to equal V total over R total. So 3 volts divided by 1.5 ohms. 3 divided by 1.5 is 2. And volts over ohms are going to give us amps, the units for current. So we have 2 amps of current that flow out of the battery. They flow out of the battery and they would go through this total equivalent resistor. But let's look back up at our picture with all of our components. 2 amps flows out, but then it gets right here. And some of it's going to go down this way. That'll be what we call I1. Some of it's going to flow through here. We'll call that I2. And some of it's going to flow through here. We'll call that I3. That current is going to have to split up to take the various branches. Now there's a total of 2, which means that all these pieces are going to add up to that total. I total is going to split apart into I1, I2, and I3, and those parts better equal the whole. All right, but we can't solve for those right now. Those I1, I2, and I3 are missing, and we're also missing the voltages, which means we can't use Ohm's law here. What are we going to do at this point? Well, we turn to our just rules about circuits. There's a special rule for parallel circuits that has to do with our voltage drops. Voltage drops are the same for parallel components. So all these components are in parallel. I know that if I leave this battery, I've got 3 volts, I better spend it all before I get home. I can either go through R1 and spend 3 volts, but then I'm home. I have to spend it all there. Or I can go through R2, but I only see R2, so I have to spend all 3 volts at R2. Or I could go all the way through R3, but again, I need to spend all 3 volts at R3. We can just drop this voltage down because we know that voltage drops are the same for parallel components. 3 volts goes in every voltage spot. That entire column drops down. Just like we were able to drop down the current column for series circuits, you can drop down that total voltage column when we're dealing with parallel circuits. Well, and at this point, we have 2 out of 3 of all of our columns, of all of our rows. So let's go ahead and come up with I. Just like I total was V total over R total, I1 is going to be V1 over R1. V1 is 3 volts. R1, 3 ohms. We're going to get I, which is a current, so 3 over 3 is 1. The unit should be amps. There is 1 amp that will go down through R1. I2 is V2 over R2. V2 is also 3 volts. R2 is 4 ohms. So now we're going to get 3 over 4, which is 0.75 amps. So 0.75 amps. And we could probably predict the next one. 1 plus 0.75 is 1.75. We know that all of them need to add up to 2 amps. This last one should be about a quarter. I say about, it should be a quarter. V3 over R3, 3 volts over 12 ohms. 3 over 12 indeed is 0.25, and the units should be amps. You'll also notice that the most current goes through the lowest resistor. The least current goes through the highest resistor, and they actually arrange themselves in perfect ratios. It turns out the electrons, as they're going through the circuit, they can look around and say, oh, hey, that path looks easier, so most of them go through that path. In fact, half of the current goes through the 3 ohm resistor. This resistor is 4 times as big. 3 times 4 is 12 ohms. We get 1/4 of the current through that largest resistor. They split themselves in perfect ratios. Most of the current goes through the easier path, but the line gets long enough to that branch. Eventually, people decide to go through the rougher patches. They're willing to take the scenic route since the interstate's clogged up, I guess. Something along those lines is the way to think about it. But the take-home point is most of the current flows through the lowest resistor, and less current flows through those higher resistors. All right, well, now that we've got all of this information, let's go back and get the powers. P just equals IV, doesn't matter about series or parallel. P total will be I total times V total. That's going to be 2 amps times 3 volts, 2 amps times 3 volts, 6 watts. We have 6 watts of power. And we can go ahead and fill in the rest of these. I times V is 3 watts, 1 times 3. I times V, I2 times V2, 0.75 times 3. That's 2.25 watts. And then 3 times 0.25 is 0.75 watts. And so does P1 plus P2 plus P3 equal P total? Remember, we don't just look at one loop. That's for the voltages, and we've already satisfied that. Each loop certainly uses up all the voltage. Do all of the components use up all of the power? So we have 3 watts plus 2.25 watts plus 0.75 watts. Sure enough, 3 plus 3 is 6 watts. It does have consistency. We've got the double check there. And we can be comfortable and confident with our solution here, and we could answer any question about this circuit, how much current goes through each piece, what the voltage drop is across each piece, total resistance, anything about power. We've got all the information right here, and we're ready to answer any question you could ask us about this circuit. All right, so I hope you guys enjoyed those. Last up is our tricky problem, a combination series parallel circuit. So don't miss it.